For example, a room full of air has a temperature, which is a measure of the average energy of motion of all the individual air molecules. But a single air molecule doesn't have a temperature, at least not in the same way. Instead, that molecule has a velocity and a mass and so on, which define how it bounces off the walls or other particles, giving rise to what we perceive as temperature, and giving rise to the laws of thermodynamics. So, we tend to think of emergent properties and laws as less fundamental than the properties and laws governing individual particles. Entropy is a thermodynamic property, and the second law is, well, the second law of thermodynamics, so is also statistical in nature. Why then are these things considered so fundamental? To answer that, we need to understand what entropy and the second law emerge from. What underlying property of nature do all these different definitions of entropy describe? As is often the case, getting more fundamental means getting quantum. And there is indeed a type of entropy that applies to quantum systems, like our air molecule. It's von Neumann entropy. And understanding it may help us understand not just the second law, but also the arrow of time, and how the large-scale world emerges from the quantum world in the first place.
Warm, humid air low to the ground moves north from the Gulf of Mexico and collides with cool, dry air high above the ground rolling in from the Rocky Mountains. The collision of air masses creates a supercell, a massive thunderstorm that has a strong rotating updraft of air.
On Nova.
Major funding for NOVA is provided by the following: the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. The Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Additional funding from Roger and Vicky Sant.
The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward towards space. As sightings accumulated, they became a part of aviation folklore, rare and unconfirmed events that hovered just outside the boundaries of real science. Until another chance sighting provided more evidence.
A fellow by the name of Jack Winkler had some detectors out. He was looking for something else, but he discovered them by accident with equipment that was operated on dark nights in Minnesota.
While testing a low-light video camera in 1989, Jack Winkler and a team at the University of Minnesota accidentally captured a black and white image that seemed to show the elusive upward lightning the pilots had described. Fittingly, this ethereal phenomenon became known as a sprite, a whimsical name that captures its fleeting nature. These giant pillars of light sparked an intensified interest in lightning and the dangers it presents to spacecraft during launch or landing. Today, astronaut Satoshi Furukawa is looking for thunderstorms. Sprites are only found where lightning is present. But spotting sprites isn't easy. They only accompany bolts of lightning over 10 times more powerful than normal lightning.